In this video, I will talk about properties of logarithmic function. In previous video, we saw that how can we define the natural logarithmic function. So the first property that we see over here is when b is greater than 0 and x is greater than 0, then the first property is product rule. Product rule says that natural log of two functions which are product of each other, b of x, is the sum of natural log of b plus natural log of x. This is the first property. So it means that these products will be distributed individually to the natural log, and we add these two functions. The second property is quotient rule. Quotient rule. The quotient rule says that if we have two functions in quotient form and we want to find the natural log of that function, then we can write natural log of b minus natural log of x. This is the second property of logarithmic function. The third property is reciprocal rule. Reciprocal rule. And the reciprocal rule says that the natural log of 1 over x will be equal to natural log of 1 minus natural log of x. And we know that natural log of 1 is 0. This value is 0 as we saw in our previous video. So this will be equal to minus natural log of x. And this can easily prove when we put b is equal to 1 over here. And the last property is the fourth property. The fourth property is power rule. Power rule. And the power rule says that natural log of x raised to power r, then the power will be written as a product. So we have r natural log of x over here, for r is rational. So these are the properties of logarithmic function. One thing I want to emphasize over here is that log and natural log, these are equal. These are equal when there is a base e. But log a is not equal to natural log. So logarithmic function or natural logarithmic function is different when we talk about different bases. Okay. Now we want to prove these properties. Maybe we start with from property 4. We know that if I take a derivative of left hand side, natural log of xr, and the answer is 1 over xr, by using chain rule, taking derivative of xr. So we have 1 over xr, and the derivative of xr is r xr minus 1. So finally we get 1 over x r minus r plus 1 r. So that is r over x. Okay, and we know that this will be equal to d by dx r natural log of x. R is just a constant, and we can just take a derivative. For example, r is outside of this derivative, and natural log of x has a derivative of 1 over x. So r over x is equal to this term over here. So what we achieved, d by dx natural log of x r will be equal to the right hand side. Since the two derivatives are same, the derivative of this function and the derivative of this function is the same, so it means that they are differed by some constant. That was the work that we have done earlier. If two derivatives of different functions are same, they are only differed by some constant r, natural log of x plus c. So here I have written this function over here, natural log of xr. R natural log of x is over here, and on the right hand side we have just added one constant. What is the reason? If you just take a derivative of this answer, natural log of xr, d by dx r natural log of x, then that derivative is 0, so these are equal. That is very simple logic. When two derivatives are same, then they are differed by some constant. This is actually a corollary in previous lectures in mean value theorem. Now we want to prove that natural log of b of x will be equal to natural log of b plus natural log of x. So in fact, we want to prove the product rule. So this is a proof for product rule. Product rule. How we define this function? So simple thing is, the logic is that we want to make two derivatives equal. And as we did earlier, we just will add some constant at the end. So take a derivative of natural log of bx. That derivative is b over bx. We apply the chain rule and we get 1 over x. And we know that this is the derivative of natural log of x. So it means that these two functions have same derivative and they will be differed by some constant. So natural log of bx will be equal to natural log of x plus c for some constant c. So it means that uh, we have proven this result, which is the product rule. Okay. Suppose if x is equal to 1, let's see what happened. If x is equal to 1, then we have natural log of b is equal to natural log of 1 plus c. And natural log of 1 is 0. So c is equal to natural log of b. Okay. In this proof here, we have just added a constant, but the actual proof was we should have natural log of b. So we can find the value of this constant when we put x is equal to 1. When x is equal to 1, c is equal to natural log of b. So then we have actually proven that the product of two functions will be written as natural log of x, the first product, and the natural log of b, which is a second product. So you don't need to just write the natural log of b plus natural log of x plus c, right? Something like that. But you have to find the value of c as well. Let me just see in the previous example as well. Here we have to, in this example, we have to prove r natural log of x not plus c, not some constant over here. So for example, when I take x is equal to 1, then this natural log of 1 will be equal to 0 plus c, so C will be equal to 0. So at the end, you get C is equal to 0. So the complete proof is when X is equal to 1, then C is 0. So then it becomes natural log of XR will be equal to R of natural log of X. So this should be added in the proof. Otherwise, it is incomplete since we don't want a constant, this constant over here. We want only this function on the right hand side. These two should be same. I think you can also prove this is just an exercise. You can probably prove some other properties as well, or maybe I have proven all over here. So I think you can do that. For example, you can easily, we already proved that product rule, the quotient rule. I think you should do it yourself. Reciprocal, you can obtain the reciprocal result from here. And the power rule, we already proved this power rule over here. So I have proved over here is the product rule, and also the fourth one, you can do the exercise and prove the quotient rule.